So in this video, what we're going to talk about is we're going to talk about finding instantaneous velocity. This is very much associated with finding the slope of a tangent line, and it's going to be a key skill that we have and that we want to develop when talking about the derivative and working with the derivative. Okay, so when we were looking for the instantaneous velocity, we found the average velocity as time intervals got smaller and smaller. Okay, and so we had this equation that the average velocity, okay, was going to equal the position 2 minus position 1 over a time 2 minus time 1. So a change in position over the change in time, or s of t2 minus s of t1 divided by t2 minus t1. Okay, basically we've done, did quite a few times actually doing that. So hopefully that, kind of that equation has become somewhat ingrained for you. Now the time interval would be t2 minus t1. So that's what we talk about when we talk about a time interval. And so what we're looking for when we look for the instantaneous velocity is we're looking for what happens when t2 and t1 get really small. What's going to occur with the velocity as that gets really small? So we're going to do a little bit of algebra. Let's suppose that x is the time that we want to find the instantaneous velocity for. And we'll let h, okay, h is going to be that time interval. It's going to be t2 minus t1. So that means that if the position function is f of t, then the position of the object at a time x is f of x, okay? So like basically, we got this position function f of t, right? It's been called s before. We'll see that again, right? But if we're looking at it at a time x, then its position at time x is f of x. So if that's the case, we need to do a little algebra, okay? Let x equal t1, then h is going to equal t2 minus t1, and that means that t2 is then going to be h plus t1. All right, so all I did was I just added t1 onto h, right? Just did a little bit of algebra. Or t2 is going to equal x plus h, right? So if you remember, we said that t1 was x, okay? T1 is x, okay? So that just makes this t2 is going to be x plus h, right? So basically what's happening here, if you kind of think about it, and you take a second to think about it, you're like, oh, okay, so what I'm going to do is I'm going to add in, right? I'm going to add my time interval onto the original value, right? So I'm going to, if I add my time interval to the original value, I'm going to get to t2, right? So like if, say for example, our time interval was 1 second and t1 was 1, then t2 would be 2. It would just be 1 plus the 1 second. Okay, that's it. That's all we're doing there. Okay, we're just going to say, okay, well, we'll change our variables around, and it's going to allow us to do our calculus a little bit easier. Okay, in fact, it makes it a lot easier than using something like the tangent line function. That'd be a problem. That gets a lot harder. So the average velocity, which we're going to call delta v, okay, and you're going to see this. Delta means change, right? Right? So we can in fact call it change in, or excuse me, actually it's delta s, okay? Which is our delta s, change in position, is, yeah, is going to be, or delta f rather, change that, make it delta f, because we're actually talking about our function f. So delta f is going to equal f of x plus h minus f of x over x plus h minus x, okay? Remember, this is t2, here's t1. This, before, if we think about it, that's s of t2, and this is s of t1, okay? So all we're doing, we're just replacing it with some different variables that are going to end up being, one, what our author uses, two, what are going to be very common for when we work with these kind of problems. So now we have f of x plus h minus f of x over h. So just a little bit of algebra in order to kind of change our equation, okay? Now to find the instantaneous velocity, then we take the limit of delta, again, delta f, okay, as h gets really small, right? And so we now have a way of thinking about this. Like before we didn't, we just had to kind of watch, we increased on our table. We got closer and closer and closer to whatever value we were looking for. We said, okay, eventually it'll be there, right? But we didn't have a real way to do this algebraically or analytically. Well, now we do. We have it like the limit. So the limit as h approaches 0, right? That's the idea of the interval getting really small. Okay? And then that's going to be f of x plus h minus f of x divided by h. All right? So it's this function, right? It's that average velocity, but then we're going to look at it as the limit of h, as the limit gets really, as h gets really, really small. So that's how we write it. We write it as the limit as h approaches 0, as the interval gets tiny. Okay? And so this is the instantaneous velocity. So let's answer our question. Let's find an instantaneous velocity. That should be kind of cool. Let's do that. Okay? So let's say suppose that an object is dropped from a 100-foot building and the object's position is then given by this function, right? So f of t, right, t being our time, equals 100 minus 4.9 t squared. What is the instantaneous velocity of the object after 6 seconds? Okay, so we're going to be asked to find that. And then what is the velocity of the object when it hits the ground? Awesome. Another good question. All right. Well, let's start out and we'll say, okay, we have an equation for the instantaneous velocity. Okay, we'll call it v, or v of t, is going to equal the limit as h approaches 0 of, in this case, it'll be f of 6 plus h minus f of 6 divided by 6 plus, or divided by h, right? Because we just want to see as h goes to 0. So we're going to have to find f of 6 plus h and f of 6. So let's suppose that an object is dropped. Suppose that an object is dropped from a 100-foot building, and the object is given by the function f of t equals 100 minus 4.9 t squared. Okay. What is the instantaneous velocity of the object after 2 seconds? What is the velocity of the object when it hits the ground? So what I'm gonna do is I'm now gonna use that equation, right? I'm gonna call it v of t, my velocity, v of t, is gonna equal, okay, f of 2 plus h, or excuse me, is gonna equal the limit as h approaches 0, right? That's our equation of f of 2 plus h minus f of 2 divided by h. And so what I'm going to do then is I'm going to say, okay, this is going to be 100 minus 4.9 times 2 plus h squared minus, right, basically 100 minus 4.9 times 2 squared, all divided by h. Okay? So we'll go in, we'll do a little bit of algebra. So what I want you to do now is I want you to see what I do algebraically, because it's kind of going to be one of these patterns that if you kind of notice it, it's going to make some of your calculations easier. And it also kind of illuminates a little bit of what happens with the derivative. So this is going to equal the limit as h approaches 0, okay? And this is going to be 100 minus 4.9 times, and this will be 4 plus 4h plus h squared, okay, minus 100 plus, and this will be 4.9 times 4, all divided by h. Okay? Now what you want to see here is, if I rewrite this again, this is going to end up being the limit as h approaches 0, okay, of 100, all right? And there'll be this 100 here, and this 100 here, okay? That's going to be 100 minus 100, okay? I've got a minus 4.9 times 4, minus 4.9 times 4, and I have a plus 4.9 times 4. And then I have minus 4.9 times 4h plus or minus again, 4.9 h squared divided by h. All right? And here's why I did that, okay? I did that because what we want is we want the h's to all go away, like the h in the denominator to all go away, right? We want this to go away. We want it to get canceled out, all right? And the reason why is because otherwise you're going to be dividing by 0, right? That's a problem for the limit. You don't want to be dividing by 0, okay? So when you're finding that derivative, you better hope that all those constant terms go away, okay? Otherwise, you've probably done some wrong algebra. In fact, you've definitely done some wrong algebra. So, well, unless it doesn't have a derivative. We'll get into that later. But you go in here and we're going to look and we're going to see, oh, that's exactly what happened. 100 minus 100, negative 4.9 times 4, and plus 4.9 times 4, right? Okay. They're going to cancel. So we're going to be left with the limit as h approaches 0 of, and this is going to be 4.9 or negative 4.9 times 4h minus 4.9 h squared divided by h. So this is then going to equal negative 4.9 times 4 minus just h, or excuse me, it'll be the limit. The limit as h approaches 0 of negative 4.9 times 4 minus 4.9h. Good news, okay? The good news is this, is that h approaches 0, so this is, right, this is a polynomial we can just directly substitute. So what we get now is this is going to end up equaling just negative 4.9 times 4, which equals negative 19.6, and in this case, it'll be feet per second. Because we're 100 feet in the air, and t is in seconds, so this is going to be feet per second because it's a velocity. Okay? And now the negative just means that it's traveling downward. Okay? If it were traveling upward, or we were traveling in a positive, what we call a positive direction, then it would be positive, but we're not, so consequently, we're going to use the negative. We're moving downward. Okay? So if we take a look at this, what we've done here is we plugged it in, the velocity, into this time function. Okay? We plugged it into the time function. And then, okay, what we do with that is then we just go and find that limit. We do some algebra. Sometimes it's a little complicated. Okay, so sometimes it's like a little tricky, but it's basically just finding a limit. It's just finding a limit and doing some algebra. Okay, and that gives us our instantaneous velocity. This function right here, okay, you are going to need to memorize it. But also notice it's basically exactly the same thing that you did with the tangent line, right? Okay, it looks very similar. And in fact, we're going to get into in just a little bit how they're really tightly connected. Now let's answer part 2. Part 2 asked what is the speed that the object is traveling when it hits the ground? So I don't know the time, right? Okay, the time when the object hits the ground is unknown, okay? So the time when the object hits the ground is unknown. So what I need to do first is I need to find the time. An object hits the ground when its position is 0. Okay, generally when we write a function, right, we start out at the building's 100 feet up, so that's the plus 100, and then it's going to drop, and so when it hits the ground, finally hits the ground, it has a position of 0. Okay, so we're going to say we want to know when 100 minus 4.9 t squared equals 0. Okay, so we're just going to go solve that equation. All right, it's just a little quadratic, so let's do that. So basically that's just going to be negative 4.9 t squared equals negative 100. Okay, then t squared is going to equal, okay, 20.40816. And so t, when we take the square root of both sides, right, we're going to end up with equaling to 4.5175. Okay? So in some of these early lectures, I'll go through and do a bunch of that algebra. But in other ones, I'm basically going to be like, okay, so I went in, I did some algebra, I solved for this. All right? And so if you're having some problems with, solving, say, for example, some quadratics, anything that's supposed to be, basic, the more basic college algebra, you and I can talk. I can send you over some videos to kind of work on it. Or you can like work with people inside of the Math Center. And that way you can kind of hone these skills. All right. So the time here when it hits the ground is 4.5175 seconds. Okay. So that's when it hits the ground. Now, all I want to do now is to find the instantaneous velocity when it does. So now let's find the instantaneous velocity. So what we're going to do is we're going to take the limit as h approaches 0 of, and this will be f of 4.5175 plus h minus f of 4.5175 divided by h. Then we'll just plug these into the equation. So we'll get 100 minus 4.9, okay? And it'll be this one, 4.5175 plus h squared minus 100 minus 4.9 times 4.5175 squared, okay? All over h, and let's not forget that we are taking the limit as h approaches 0. Now this thing, the cool thing is that the 100s are going to go away, okay, as is the 4.9 times 4.5175 squared, right? We want to make sure, but, when I multiply it out, we'll see that that's the case. So this is now going to be the limit as h approaches 0 of 100 minus, and this is 4.9 times, and this will be, I'm just going to write this as 4.5175, that'll be squared, right, plus 2 times 4.5175 times h plus h squared minus 100 minus 4.9 times 4.5175 squared. Now when I separate it all out, notice that we're going to distribute that negative, so this is going to make this one a plus, okay? So that's going to actually eliminate, and then we're going to divide by h, excuse me. We're going to end up, in this next term, we're going to eliminate, 100 is going to go away, the 4.9 times 4.5175 squared is going to go away, so we're going to end up with the limit as h approaches 0 of, and this is going to be negative 4.9 times, right, we'll multiply by 2 times 4.5175 h minus 4.9 h squared, because that's all we've got left, and we'll divide it by h. So now, when we divide by h, that's just going to give me then the limit as h approaches 0 of negative 4.9, or actually, let's just do the multiplication here. Negative 44.2715, right? Because my h's are now going to cancel, right? Minus 4.9h. Since this is a polynomial, we can actually just substitute in the h equals 0. So we are left with that this thing here is going to equal negative 44.2715. And that in feet per second. And that is the velocity of the object when it hits the ground. Cool. So what did we do for the second part? Well, the first piece that we did there was we actually had to figure out when the object hit the ground. And that's solving the equation of when our function ends up equaling 0. So that's when the object hits the ground. Then I went in and I used my equation for instantaneous velocity, right? I went out and I found the limit, right, of f of x plus h minus f of x divided by h as h approaches 0, and that gave me my instantaneous velocity. Let's do one more example. Let's suppose that a car is traveling down a road and its position after t seconds is s of t equals 18 t squared feet. So that's its position function. How fast is the car traveling after 20 seconds? Okay, so we're going to just use our velocity function. And we want to know that v of t is going to equal, okay, it'll be s of t plus h minus s of t all divided by h. And we're going to be looking for that, the limit as h approaches 0. So our velocity function is going to be the limit as h approaches 0 as s of t plus h minus s of t divided by h. So all we did was we changed what we called the function, okay, and we changed the variable. We called it t now, okay, instead of x. All right. So when we plug in our values, that's actually going to be, right, it's going to be it's going to be the limit as h approaches 0 of s of 20 plus h minus s of 20 divided by h. Okay? And that then is going to equal, right, 18 times 20 plus h squared minus 18 times 20 squared, all divided by h, and we want to find the limit as h approaches 0. Okay? Now, remember, we're expecting that this piece is going to go away, and it will. You'll see just in a moment. So this is going to end up being 18 times 20 squared plus 2 times 20h plus h squared minus 18 times 20 squared, all divided by h. And again, we're still looking as the limit as h approaches 0. Okay? Now what you can see is the 18 times 20 squared, they're going to go away, and we're going to be left with the limit as h approaches 0 of 20 or 40h, excuse me, 40h times 18, right, plus 18h squared, all divided by h, right? I almost forgot that 18 that's sitting right there. Almost crossed that out too. Remember, it's got to be distributed to the entire function. Okay? And so this is going to be the limit as h approaches 0 of 18 times 40, 720, plus 18 when we cancel out our h's, right? Okay, 18h, excuse me. And since we're looking for the limit as h approaches 0, that goes away. So this ends up being 720, or 720 feet per second. All right, so that's how we find instantaneous velocity. A couple of examples, a couple of problems that you might actually see, and how it is that we go from like that slope of the tangent line or the average velocity to this instantaneous velocity function. Really important, right? Okay, this function here, okay, this thing here, this process here, right? You need to memorize it. Yes, and you need to get comfortable with actually working with it. It's very, very important, right? We're going to see it all over the place. Now, in addition to that, okay, no, there's no addition to that. Okay, so this completes the lecture.